Okay, this is about finding the null space of a matrix A, any matrix, square or rectangular. And what does that mean? That means, well, in algebra, we're solving the equation AX equals 0. So A is our matrix, X is a vector that we're looking for, and AX is a combination of the columns of A. So we're looking for combinations of the columns that give the 0 vector. Dependent columns, we'll be saying. So that's the goal. The new start for linear algebra that I've suggested solves that problem for small matrices. Kind of just does it for a small matrix. But for any matrix, or a big one, we need a system. So this kind of completes the idea by giving the system, which uses the algorithm of linear algebra, which is elimination. So elimination is going to be the key to solving this problem, to finding the null space. So that's my picture. Oh, these are I'll just mention the 3 books which discuss this. The one on the Introduction to Linear Algebra is the main textbook. Then the Learning from Data book, actually that's where this new idea got started, and the Linear Algebra for Everyone has got the idea in more completely. So I'm sort of speaking about a section out of that a 3rd book. Okay, and they all have websites, math.mit.edu. The addresses are there to see more. Actually, I should say, so these are the key ideas of this lecture. And yesterday I looked at my lecture from a few years ago, quite a few years ago, lecture 7 in the OpenCourseWare series for Math 1806. So that was on the same topic, elimination and AX equals 0. So a lot of good stuff is there. But there's a little more to say now, and that's what this is about today. So, okay, here are key ideas of the lecture. So the null space, so now you see it in writing, the null space is all the solutions x to AX equals 0. Remember, x is a vector. And elimination is the key, and it keeps the same null space. And the MATLAB command is RREF of A. That's the command that does elimination. And we'll see the identity matrix. We'll see a matrix F. And the new idea was to factor the matrix into a column matrix C times a row matrix R. So this is really putting all the ideas together. And we learned that if a matrix is short and wide, then there's certainly, if we got lots of columns, then some of them will be dependent, and that means that there'll be solutions to AX equals 0. So here we go. Oh, okay, I'm going to start with an example. And it's already been, elimination has already done its job. So what elimination did was to get to that, you see the identity matrix in the first 2 columns, 1, 0 and 0, 1. So that's, you can't ask for a simpler matrix than that. Once we've got that, we can't mess with it. So 3, 5, 4, 6, we're stuck with, those are our other columns. So the first 2 columns are independent. Columns of the identity matrix are very independent. But then 3, 4 is a combination of those 2 columns, right? 3, 4 is 3 times the first column plus 4 times the second. So there is an X in the null space. That's one of the vectors we're after. I'll call it a special solution because it just came specially from one column. And you see it down below as S1. So we would take, if we took -3 of the first column, -4 of the second column, and then +1 of the third column, we would have 0. AX equals 0, what we're looking for. And the second special solution would come from the last column of the matrix, 5, 6. So that again, that's 5 of the 1, 0 column and 6 of the 0, 1 column. And if we put that together into a special solution S2, we want minus 5 of column 1, minus 6 of column 2, plus nothing of column 3, plus column 4, giving 0. So in this case, elimination has produced this simple matrix R, simple because it's got the identity there. So can I show you one more example of R before I begin to talk about how do we get to R? Okay, so here's another R. A little different though. It's different because it's got a row of zeros. Well, that won't pose any problem, but we just have to think what to do with it. We always move 0 rows to the bottom, and there it is. And it does have an identity matrix, as the first example did. But you see that the 1, 0, the 0, 1 is off in column 3. The identity is in columns 1 and 3 here, and that makes a small change. But the idea is still the same. Those two columns are the independent ones. They're very simple. The 1, 0, 0 and 0, 1, 0, those are totally different directions. Then the 7, 0, 0 is 7 of the first column. So that's spotted a special solution in X that I call S1. At the bottom line, you see the minus 7 of the first column plus 1 of the second column produces 0. You just look at those columns. Minus 7 of the first plus 1 of the second, everything cancels. And the other one is going to come from the 8, 9, 0 column. That'll be 8 of the first column and 9 of the third, the 2 bits of the identity. So you see that when we get to this reduced row echelon form, horrible set of words, but what it means is elimination has made it as simple as it can be. Okay, I might have something more to say. Yeah, so this is summarizing what you've just seen. So we have the simplest case where the identity just sits there at the left, or the more general case where the identity is mixed in with the other 2 columns. We can live with both. And I'm using F for the other columns, the columns that are not part of the identity. And then it has that extra 0 row. Okay, and now I want to write it. A key part of this lecture is to see the result, this matrix R see it in matrix form instead of a bunch of numbers. Often in the computing, you're just pages full of numbers and you don't see what's happening. So what we're looking for is the identity matrix and the non-zero matrix F. And now in that R0 case, that second example, there's a P. What is that matrix P doing there? Well, it's a permutation matrix, an exchange matrix, because the identity in this second example is not in columns 1 and 2, it's in 1 and 3. So that P has to put it there. So that P is and because P is on the right, it'll do it'll move columns. And there I wrote down what that P is. That exchanges column 2 and 3 and puts the identity in where we want it. Okay, so that's the linear algebra, the matrix notation part. Oh, and this is here. Now you're seeing the new start, this C times R. So that's what I'm suggesting, that if you give me a matrix, the first thing I would do would be to find independent columns. Those would go into C. And then the matrix R would, well, we've seen the matrix R, and that would tell me the combinations of those C columns to get A. Yeah, you'll see it. Well, this box is around all the matrix formulas. So we're sorting every matrix into independent columns followed by dependent columns, and then this permutation, this exchange matrix P if they don't really come in that order, if we need a new order. So all this is about A equals CR, the new, well, not new, not completely new, I'm sure, but it's a factorization of any matrix. Okay, and now how do we actually do it if the matrix is big and I need the computer to help? Well, we do it by elimination. Okay, this is what elimination is about. What are we allowed to do in elimination? We don't want to mess up the equation AX equals 0. I'm operating on A, but I'm not creating or losing any of those solutions. So if I subtract one row from another row, or any multiple of one row from another row, that's the main operation of elimination, and that's obviously, the equations are still true. If I take 3 of equation 1 away from equation 2, I still have a correct equation. And I could multiply a row by 15, or any non-zero number, no change. And I can switch any 2 rows. That third one of switching rows, exchanging rows, is just to move the 0 row down to the bottom. This is the example. Can you see those numbers? So I'm giving an example of a matrix that leads to that very same R that we worked out. So you see what I'm doing now. I'm backing up. I know the R I want, but I'm given some matrix A, and it's these elimination steps that will lead me to R. Okay, so you see A over on the left? So it's a full matrix, 8, no identity there, but I'm allowed to do elimination. I'm allowed to do these 3 steps when I want to. So what shall I do? Probably at this point you've seen elimination as much as you want to, but allow me to say it once or twice more. So I would take 3 of row 1 away from row 2. That would produce, that 3 that's in the original matrix would turn into a 0. So can you take 3 of that first row? That would be 3, 6, 33, 51. I subtract it and I get just that 0, 1, 4, 6. So I've got a much better second row. Now I'm going to use the second row going upwards. So I'll take 2 of that second row away from the first row. That'll knock out the 2 that I don't want. And it'll produce the identity that I do want. So do you see that? If I take 2 of that last row, that's 0, 2, 8, 12. When I take 0, 2, 8, 12 away from the top row, I'm left with 1 and 0, and 3 and 5 are the numbers that happen to be left. Okay, that's, so really what has elimination done? This is an important idea that I think I never caught on to when I was learning linear algebra. Elimination has found the inverse of this 1, 2, 3, 7, of this 2 by 2 matrix, because it's started with 1, 2, 3, 7, and it's ended with the identity. So it must have inverted that matrix. And then when it had to apply the inverse to the second half of the matrix, and that produced the 3, 4, 5, 6. So you see, this is, look, I think there's probably an example that leads to number 2. Here, I must have thought ahead. So it says on the screen what I just said, that elimination has inverted the leading matrix. And then it's written out the step H equal WF that connects the original dependent columns to the final dependent columns in F, 3, 4, 5, 6. Okay, I think elimination is just a matter of practice, and you probably have done it. And here's an important point about elimination. That you could do things in different orders. I did them in a sort of natural order, but you could do it other ways. But you wouldn't get a different outcome. You'd get the same matrix R. Well, because the equations are still true at every point. The x's, the null space of the matrix, is not changing by my elimination steps. Yeah. So let's just repeat that when you finally get to R, when you've done the elimination and you get to R with its identity matrix, that identity matrix in R tells you which columns at the start were independent. So that's what you need to have a way to do that. And now we have a way. In the other opening talks in this series about the new start, the matrices were nice and small. So I didn't need much of a system. I could practically wing it. But now we need a system. And of course, if we want to use the MATLAB or other code, it has to have a system. So anyway, we now have a system of row elimination steps, and we know what it ends with. It ends with an identity matrix of the right size, a matrix F, that's the other columns, and then possibly a permutation to tell us the order. That's elimination. Okay, and here's the second example. So we're moving along. This is like, you got to pay attention, because this is all there is two examples, and then put the ideas together. So here's an example of a matrix A with numbers as big as 97. I don't know how I got there. Okay, so there are no zeros in the original matrix A, but elimination aims to get zeros. Oh, here it got zeros very quickly, because the second row of that matrix, 2, 14, 6, 70, that's just twice the first row. So when I subtract 2 times the first row from the second row, I get that 0 row. So I'm now one step along with a row of zeros. That's great. And the third row improved too, because I took 2 of the first row away from the third row, and that gave me a 0, 0 at the start, and then a 327. So are we okay that we're at the second matrix now? It's not finished. It's not in its R form, in its echelon form, but it's a lot closer. Okay, so what do we still have to do? Well, I look at that 3, and I'm looking to get the identity matrix. So I'll divide that. Sooner or later, I'm going to divide that last row by 3 and get 0, 0, 1, 9. But another thing I want to do is clean up the first row. So I subtract that last row from the first row. You see that? See, I'm much closer to the identity. So I'm now moved on to third matrix. And if you've done a lot of these, you know what I'm doing. I'm working a column at a time. But notice, column 2, I can't do anything with. Column 2 is a dependent column. It's 7 times column 1. I can't improve column 2. But I can improve column 3, and that's what we do. Divide that third, that 0, 0, 327 by 3, and exchange rows. Then you see that the result is the R0. So it's the R0 with the 0 row. Yeah. So that, just to repeat, this is a matrix A that leads through the steps of elimination, which we're like remembering, to R0. So we're really finished with this matrix A, because this shows how to get it to R0. And then we've already seen with R0, we figured out which were the special solutions, the vectors in the null space. So we're good. We really have done the job. And it remains to just like see a little bit, what did we do? And what's going on with these columns, these other 2 columns, the F columns that are not the identity. And you see what we've done is, well, we ended up with we started with columns 1 and 3. Yeah, so that's our matrix C. Those are the two independent columns. How do I know? Where did C come from? Because that's part of this search. Where are the independent columns? They're the ones that end up with the identity, because the identity is a way to go the right independent columns. So they're columns 1 and 3 of the original matrix. So you see C there, 1, 2, 2, and 3, 6, 9. Then F is the part of R from the dependent column, so that's the 7, 8, 0, 9, and then I'm seeing the dependent columns. Yeah, you have to do this a few times, but all the ideas now are and there I've put it together. So the idea is, with a small matrix, like only 3 columns and maybe only 2 rows, we could find C and R almost by sight. But now, even where we're up to 4 columns and 3 rows, we need a method, and that's the point of this talk, and it was also the point of lecture 7 in the original 1806, Math 1806 on OpenCourseWare. Okay, so we've found C and R. Good, good. I think it's just congratulating ourselves from here in. These are remembering the special solutions. Oh, and then why not? You remember those? Second column was 7 of the first column, so that gave that special solution, that combination, to give 0. And then the other combination gave the 0 vector. So we've got 2 special solutions. And here's the general principle. Yeah, it's very simple. After you've got this matrix down to identity and F, then the solutions X should have a minus Fi. You remember the minus signs that we saw? So all I'm saying here on the first line is that the matrix IF times minus Fi gives the 0 matrix. Of course it does. And then the second line is the little bit of special trick that you have to do if there's a P, a permutation, an exchange involved here. When the identity matrix is not sitting where you want it, you have to have a P to put it there. Then P transpose has to come into the solutions. Yeah, because P times P transpose. So remember about permutation matrices. Linear algebra is about learning different special character of different matrices, and permutations are just take the identity matrix and mess around with the rows, or mess around with the columns. Same thing, and then P transpose unmesses it, brings it back to the identity. So P times P transpose is the identity. Okay, so we're just about there. Oh, then this is the little point I made. Well, it's an important point. Suppose I have 5 columns and only 3 rows. That means I've got 5 unknowns and only 3 equations. So there are going to be solutions to that. There are going to be solutions other than the 0 solution. I can always the 0 combination will surely give 0. But if I have 5 unknowns, 5 columns in A, and I have only 3 equations, 3 rows, so 5 greater than 3, n greater than m, then there will be some columns in F, there'll be some non-zero solutions, and these examples show. So take that matrix M at the end there. You see there's a matrix with 4 columns and only 2 rows. So I've got 4 vectors in the plane. If I have 4 vectors in the plane, there are combinations that give 0. They can complete triangles. So in that case, the rank would be 2. So we're really seeing this part of linear algebra to simplify the matrix by elimination, so that all the main facts are clear. Yeah, and I'll just, oh, here's, if you really want to see it in shorthand, I'm not necessarily pushing this last idea, but if you want to see it in shorthand, we could think of the matrix as having just 4 blocks. So it's a 2 by 2 matrix, but unfortunately each of those guys is a block. So W is the one in the corner that we talked about earlier that gets inverted. So if you look at the last line, that W in the corner, that ended up as the identity. The second block row, the JK, ended up as zeros. And the one remaining guy, it tells us the combinations that we are looking for is this W inverse H, because so let me look at that equation in the box. WHJK, that's the matrix I'm starting with. I'm going to invert W, and I know that JK is some combination of WH. So when I invert W, I get the first, elimination produces a first row, starting with the identity. And when I apply that to the second, the JK row, those go to 0. So that's what elimination is doing in a real shorthand. It's taking a 2 by 2 block matrix to that matrix R at the end with a 0 block row and an identity block in the upper corner. So that is elimination and the solution of, and finding the null space. So really this completes the job of the first topic in linear algebra, is identifying, understanding these 4 fundamental subspaces, the null space being one of them, the column space being another. We understand now which columns are independent, and the row space being another, and so we're really understanding the idea of these 4 fundamental subspaces that go into the big picture of linear algebra. So this completes the first major stage of a linear algebra course. And then what's to follow is will come eigenvalues, singular values, applications of all kinds, least squares. Good math. And thank you very much. So that's my summary of finding the null space. Good.